all of you welcome to the session. Today we are going to talk about entropy. So you know that till now we haven't listened this word entropy, that is new word. Now we are talking about that entropy. Let us see what is entropy. See, there already we have discussed. So temperature of a body remains constant in an isothermal process. Yes or no? We know that in isothermal process, which one is constant? Temperature. Temperature is constant. But there is heat transfer takes place from system to surroundings and surrounding to the system. So whereas no heat is added or taken from the system in adiabatic process. So what happened in adiabatic process? There is no heat transfer takes place from system to surroundings and surrounding to the systems. Right? When a gas is compressed adiabatically, when the gas is compressed adiabatically, temperature as well as heat energy are increased. So we know that when the gas is compressed adiabatically, its temperature is raised. Its temperature is raised. That means where the heat energy also increased. On the other hand, when the gas is expanded adiabatically, heat energy as well as temperature are decreased. We know that when it is expanded, so there is no heat transfer from the system to surroundings and surrounding the systems. As a result, what happened? Its temperature decreased, right? So subsequently its heat also reduced. Right. So this shows that in adiabatic process, neither the heat nor the temperature remains constant. You must remember this word. In adiabatic process, till now we have seen that in adiabatic process, neither the heat nor the temperature remains constant. But whereas in isothermal process, temperature remains constant but heat is variable. Okay, you have to put this concept in your mind. So now the Clausius showed that there is something which remains constant during adiabatic process. Just like in isothermal process, temperature is constant. Similarly, Clausius showed that some physical quantity is also constant in adiabatic process, just as temperature remains constant in isothermal process. This constant property is termed as entropy. That constant property is termed as entropy. You must remember entropy. Let us see what is entropy here. The thermal property of a body which remains constant. The thermal property of a body which remains constant during an adiabatic process is called as entropy, which is denoted by S. See there, the thermal property of a body which remains constant during an adiabatic process is called as entropy. Right. Here one figure is there. See there, that is pressure versus volume PV diagram. So what we call it, this one is PV diagram. See there exist two cycles A, B, C, D, A, and also one more cycle is there. You have to see this picture carefully. See there exist two adiabatic curves. A and B represents adiabatic curves, and where T1, T2, T3 represents isothermal lines. Understand? Where A and B both are adiabatic lines, and T1, T2, T3 represents isothermal lines. Okay. Let us see what we have to do here. So from figure, T1, T2, T3 represents isothermals. A and B are two adiabatics. The adiabatics cut the isothermals at A, B, C, D and E, F, that which are the points, intersecting points given in the picture. Okay, so consider a reversible Carnot cycle. Let us consider a reversible Carnot cycle ABCDA. So for its working substance between the temperatures are, what are the temperatures here? T1 and T2. Suppose Q1 be the heat taken at temperature T1 and Q2 be the heat rejected at temperature T2, then T1, T2. Here, so you have to see there's something is missing here. Okay. Okay, then Q1 by Q2 equal to T1 by T2, or this can also be written as Q1 by T1 equal to Q2 by T2. Similarly, so already we got that one. 1 minus, you know that efficiency can be written as neta is equal to 1 minus Q2 by Q1. Then it can also be written in 1 minus T2 by T1. Where with the help of that equation here we'll write Q1 by Q2 equal to T1 by T2, or Q1 by T1 equal to Q2 by T2. Similarly, where if you apply whole picture PV diagram, so where we'll get Q1 by T1 equal to Q2 by T2, and also Q2 by T2 equal to Q3 by T3, that is equal to, that can also be written as Q by T, that is what, constant, right? So therefore here we'll see few points. The quantity Q by T is a definite thermal property of working substance and is termed as entropy. The quantity Q by T is a definite thermal property of the working substance and is termed as entropy. Entropy is a definite function of the internal state of a body. Okay, it is a definite function of the internal state of a body. Entropy is a definite physical entity like pressure and volume, but there is nothing physical to represent it. See there, it is a very important point. Entropy is a definite physical entity like pressure and volume, but there is nothing physical to represent it. The measurement of absolute entropy of a substance in any situation is not possible. Only measure the change in entropy as the substance moves from one state to another state. See there, have to focus on this point. When the substance moving from one state to another state, then only we can say that entropy, change in entropy word. So, but we can't say entropy, absolute entropy of a substance, right? So let us see here physical significance of entropy. The entropy of a substance is a real physical quantity and is a definite function of state of body like pressure, temperature and internal energy, etc. See there, change in entropy can also be written as heat energy by temperature, where change in entropy into temperature can also be written as heat energy, and this is just like similar to potential energy equal to mgh. Potential energy equal to mgh, where potential energy is directly proportional to mass into height, where comparing the above equations, temperature equivalent to height, then entropy corresponds to mass and inertia. Hence, entropy may be thought of as a quantity which bears to heat motion, a similar relation as mass base to linear motion and the moment of inertia in rotational motion. Entropy is also termed as thermal inertia. Entropy is also termed as thermal inertia since more entropy results in less amount of heat energy being converted into work. Thus, increase of energy of a system implies transition of thermal energy from more available to less available from the conversion into work. See there, entropy is also a measure of randomness or disorder of molecules of a system. The increase in entropy implies a transition from more ordered arrangement of molecules to less ordered arrangement, that is from order to disorder. Simply we can say that, one thing, so entropy is nothing but a disorder. You have to put this concept in your mind. Entropy is nothing but disorder. See, for example, when the water is converted into ice. So when the water is converted into ice, what happened there? So atomic arrangement is when the water is converted into ice, where the atoms are arranged in regular order in case of ice comparing to the water. So in the case of water, atoms or molecules are moving state, right? They are random. So that means when it is converted into ice, when the water is converted into ice, whose entropy is decreased. That means what happened there? Inorder state to order state. It is converting inorder state to order state. That means where the entropy is decreasing. Otherwise, when the ice is converted into water, where the order state, what is happening there? Where order state is converted into inorder state. That means what happened there? Where the entropy is increasing. Simply we can say that while the class is running, all the students are sitting in their proper places on the table, right? So then what happened after the class work? After the college time, what happened? You may stand up and just go outside the classroom. So at the time, what happened? Where the entropy is increasing when you are moving out of the class, right? That means what happening there? There we can get order state to inorder state. When the order state to inorder state takes place, entropy increases, right? So this is the little bit concept and physical significance of entropy.